Okay, Algebra 2 guys, this is linear programming. Now there's a lot to this, so there's probably a fair chance that I'll break it up into two parts and notes. So linear programming. So what you're looking at is kind of putting many real life problems into a context and finding what's called optimization, which is basically what is my best way to go about doing something. So a linear programming model consists of a system of restraints, which is, in our terms, a set of linear inequalities, and an objective function that can be minimized or maximized. So what we're trying to do is a couple things. One, we are trying to graph the systems of constraints. We're trying to figure out what we call a feasible region, which in this case is kind of this shaded area right here. And when you do that, points emerge. All right, and when you get those points, you want to put those values into an objective function and either try to get the highest, get the maximum, or get the minimum. All right, so we're trying to figure out a feasible region, look at the vertices, and then figure out if we can maximize or minimize it. All right, so let's kind of walk through one simply here. So you've got x greater than or equal to 1, y greater than or equal to 0, 2x plus y less than or equal to 6. Here's my objective function. I want to figure out the maximum and minimum values for the function of this region. So we sketch a quick graph. X greater than 1 means this is solid. And I'm going to shade this way. Y greater than or equal to 0 is right here. Shading is going to go up. This last one, which will be this color, if I just do a little algebra, negative 2x plus 6. So I'm at positive 6. I go down 2 over 1. There's my line, solid line. And that's going to be shaded down this way. So my feasible region is this area right here. This little triangle. So now this little triangle is created by 3 points. So what I want to do is look at those 3 points. 1, 2, 3. So I've got 1, 0. I've got 3, 0. And I've got 1, 4. So now what I do is I put each one of those into my objective function and see what I get. So this will be 3 times 1 plus 0, which will be just 3. This will be 3 times 3 plus 0, which will be 9. This will be 3 times 1 plus 4, which will be 7. So this one will be the minimum. This one will be the maximum. So now you will only look for one. You won't look for a minimum and a maximum. Most of the time you're looking for a minimum or a maximum, just one. A lot of times what you're looking at is if you're trying to minimize costs, you will look at some restraints and you'll look for a minimum. If you're trying to maximize profit or maximize efficiency, you're going to be looking for a maximum. So that's kind of what we're talking about here. So let's take a look at this one. The objective function 2x minus 3y. My constraints are x less than or equal to 2. So x less than or equal to 2 is here. That's going to shade this way. The second one, which will be in blue, so if I do this, that's negative y minus 3x minus 2. So getting rid of changing all signs. That changes this sign as well. Y less than or equal to 3x plus 2. So that's going to look like this. And that'll be shaded towards 0. Then my last one, y equals x minus 2. That's going to be right here. And that is straight diagonal. So now the question becomes, am I shading down or am I shading in the middle? Well, 0, 0 here is 0 greater than or equal to 0 minus 2. Yes. So my feasible region is going to be right here. So my points are going to be right here. So that's going to be -2, 4. I'm going to have one more here. That's going to be at 2, 0. I'm going to have one up here, which is actually going to be at 2, 7. Or, I'm sorry, that's going to be 2, 8. So you're trying to figure out those three values. You're trying to put them in and figure out what is my maximum, what is my minimum. So my first one, 2 times -2 minus 3 times 4. That's going to be -4 minus 12, -16. That might be a winner for the minimum. This one, 2, 0, 2 times 2 minus 3 times 0. So that's going to be 4. This last one is going to be 2 times 2 minus 3 times 8. So that's going to be 4 minus 24. That's going to be -20. So here's my minimum. Here's my maximum. So if you want to put in words, 1, define the variables, write a system of inequalities, graph that system of inequalities, find the coordinates of the vertices of the feasible region, write the linear function to be maximized or minimized, substitute the coordinates into the function, and select if you want the greatest or the least result and answer the problem. So we got a problem like this. We're receptionist for a vet. One of Dolores Alvarez's tasks is to schedule appointments. Let me move this guy. She allots 20 minutes for a routine office visit and 40 minutes for a surgery. The vet cannot do more than 6 surgeries per day. The office has 7 hours available for appointments. If an office visit costs $55 and most surgeries cost $125, how can she maximize the income for the day? Okay, so step 1, define the variables. Well, we got 2. We've got appointments and we've got surgeries. So in the context of the problem, X is going to be appointments, Y is going to be surgeries. So now let's start writing kind of some equations here. Well, the first one is easy. You can't have a negative appointment, so they've got to both be at least bigger than 0. All right, you can't have a negative surgery. You can't, undo a surgery. You can't put something back in. The other one is this. The veterinarian can't do more than 6 surgeries per day, so Y has got to be less than or equal to 6. The veterinarian cannot do more. The office has 7 hours available for appointments, and then each 20 minutes for an office visit and 40 minutes for a surgery. So that's going to be 20 minutes for an office visit, so 20x, plus 40 minutes for a surgery. It's got to be less than or equal to, not 7, because it's in minutes, 7 is in hours, so I will take 7 times 60 and go 420 minutes. So now let's do a quick look. Do I have any other ones to go off of? Not really. So X is 0, Y is 0. Let's take a look at our graph here. So Y is less than 6. All right, 20 plus 40Y is less than or equal to 120. So a little bit of work. $420 divided by 40, that's going to be 10.5. All right, so let's graph this. 10.5, 6, 7, 8, 9, 10, 10.5. We're going down 1 over 2. So I'm being very, very picky about my graph because I want to be able to read it pretty well. and that's going to be down and in as well. So these are kind of my two ideas here. So I can do 1, 2, 3, 4 vertices. All right, obviously, so this one's 0, 0. And what this represents is no appointments, no surgeries. It was a very dull day. This one is 0, 6. And kind of what that means in the context of the problem is that you're doing no appointments and you're doing 6 surgeries a day. All right, this one, 9, 6, says you're doing 9 appointments a day and 6 surgeries. And this one, 5, 10, 15, 20, 21, 0, is saying you're doing 21 appointments, you're doing 7 hours straight of appointments, and you cannot do any surgeries that day. So that's my feasible region right here, because this is it. So now we've graphed. So let's find the coordinates of the feasible region. We did that. Step 5, write the function to be maximized or minimized. So that's where we go back to this last statement here. Office visit costs 55, surgeries cost 125. We need to maximize the income for the day. So the function is going to be 55x plus 125y. And we're looking to maximize that. So we're looking to figure out what is going to be the best use of our day to make the most amount of money. So you can eliminate 0, 0 because we know that's not going to get it done. All right, but we got to check the other one. So if I go 0, 6, so if I go 125 times 6, that's 750 bucks. So here, if I put that in, that's 750. Let me get rid of this. So if I go 9, 6, that's going to be $1,245. So that's going to be $1,245. Now the last one, if I go 21, 0, that's this point right here. That's 1155. So the best situation for me is to do 9 appointments a day and 6 surgeries a day. That's going to be my maximum. So take a look at this one here. The landscaper balances his daily projects between small landscape jobs and mowing lawns. He allots 30 minutes per lawn, 90 minutes per small landscape job. He works at most 10 hours a day. The landscaper earns 35 per lawn, 125 per landscape job. He cannot do more than 3 landscape jobs per day and get all the mowing done. Find the combination that maximizes his income. All right, so we've got 2 things here. Hopefully you guys are starting to pick up on this. So you've got mowing lawns and you've got doing landscape jobs. So we'll call X the landscape jobs, and we'll call Y the mowing. So step 2, let's write our system here. Well, easy ones are you got to be bigger than or equal to 0 for both of them. You can't do negative in there. You can't go back and make grass grow. And you can't take apart landscaping jobs. That doesn't make you any money. So here's kind of what we're limited at. He knows he can't do more than 3 landscape jobs a day. So we're limited on that. The last one is time. So 30 minutes per lawn, 90 minutes for landscape job. So if I go 90 minutes for a landscape job and 30 minutes for a lawn, that can only be up to 10 hours, but it's got to be in minutes. So 10 hours is going to be 600 minutes. So there's my limit. Okay, so there's my limits. So let's graph this. So now, let me clear this up a little bit. Let me clean this one up a little bit. So 30y less than or equal to negative 90x plus 600. So y less than or equal to negative 3x plus So I've got this line, this line. Those are my two biggies. So I know that I'm going positive, positive. Remember, X is landscape jobs. This one's the mowing. So here's what I'm looking at. 1, X has got to be less than or equal to 3. All right, so well, let's clear this up a little bit. Let's go every 2 blocks is 1. So every 2 squares is 1. There's 1, there's 2, there's 3. Ooh, let's make that straight. So that's got to be less. The last one is negative 3x plus 20. So nope, can't do that. So this is going to be, ooh. So this is going to be 3. And 20 with a slope of negative 3. So down 3 over 1, down 3 over 1, down 3 over 1. Right there. So this is going to be my feasible region right here. So my points there are going to be right here. So you've got 0, 0, which represents doing nothing, taking the day off. You've got 3, 0, which means I do landscape jobs and nothing else. I've got 3, 11, which means I do 3 landscape jobs and mow 11 lawns. Or I've got 0, 20, which says I do no landscape jobs and I just mow all day. So there's a feasible region. There are my points. So there's step 4. Let's look at step 5. We got to maximize the function. I'm going to erase this part. The function, once again, is profit. It's what are we looking at? So lawns mowed, completed landscape jobs to maximize the income. He makes $35 per lawn, and he makes $125 per landscape job. So we're trying to maximize that income. So what we want is 35 times X plus 125Y. So obviously this one's out by the fact that we have 311, 3 zeros out. So it kind of boils down to, does it make, oh, I flipped that around. Ooh. Should be 125X plus 35Y. Anyway, that's where I'm at. Sorry about my mistake. So 125 times 3 plus 35 times 11. That's going to be if I do 3 landscaping jobs plus 11 lawns. So if I do 3 landscaping jobs and 11 mowing jobs, I get $760. If I do no landscaping and I mow 20 lawns, that's going to give me $700. So what's my best bet? The best time for me, the best way to use my time is to do 3 landscaping jobs and 11 lawns in one day. All right, I'm going to call that the end of part 1. I'll do the end. I'll take a look, keep going with number 2, and we'll go from there.